All right, so today we're going to start chapter 6, which is the definite integral, and we're talking here in section 6.1 about estimating with finite sums. The big idea with this chapter is going to be that we're looking to find the area of the region underneath a curve between the x-axis and the curve. And that provides us with some applications. So let's consider this elementary problem here. We have a train that moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled by the train? Okay, not a terribly difficult problem. You all could probably figure that out. If we use the distance equals rate times time, we could get 150 miles, right? You'd get 150 miles as your answer. Okay, what if we graph the velocity function from t equals 7 to t equals 9? Well, that would look like this. Okay, we've got our time axis here, and we're looking at the time axis from 7 to 9, and our function would be just y equals 75, or v equals 75 in this case, v of t, velocity, as a function of time, equals 75. And if we were to calculate the area of this region under the curve right here from 7 to 9, that would be, this distance is 2, and then this distance right here is 75, and 2 times 75 is 150. So the distance, the area of that rectangle would be 150, which we know to be the distance traveled. So the area under the velocity curve gives us the distance that something is traveling for that particular time, on that particular interval. Okay. All right, so now what if the train's velocity changed and it was a function of time? What if it was something like this? This region's no longer rectangular, so how can we find the area in order to find the distance traveled for this particular object? It's going to be a little bit different to do that. And that's where we're going to use approximations. We're going to look at several different ways to approximate this area. One way to do this is to actually take and set up little bitty rectangles underneath the curve. We have to pick a height for the rectangles. We have to pick out how high the rectangles are going to be. So you could do one where you're using the endpoints of each of these little bitty mini intervals here between 7 and 9. And maybe we're using the left endpoints for those. And we would do a whole series of little tiny rectangles. And the more rectangles that we do, the better our approximation is. We could add up the areas of these rectangles. Okay. I'm not very good at drawing these, but these would need to be of a uniform width. The height of the rectangles would be values actually on that function. As you can see, we missed a little bit of area there, but we had a little bit too much area right here because our rectangle goes outside the curve a little bit right there. The idea is that hopefully we would do enough of these to where we would offset the underestimated parts and the overestimated parts. They would offset each other, and we would get really close to the actual area under that curve. We could also use the right endpoints of these. Then, then our rectangle would have went up higher here. We would have been over the curve on this end, and over here we would have been under the curve. We could also use midpoints of that region as estimates. And then you get a little bit over, a little bit under, and hopefully that offsets and you get a better estimate with that as well. Okay, so that brings us to our definitions of some of our approximation methods here. Rectangular approximation methods is what we're looking at here. Okay. You don't have to necessarily read those pages. I think it's really good to read those pages though. So I would go ahead and do that actually. I know I said you don't have to do that necessarily, but I think it's a good idea to read those. But you'll see that I used the example from, especially on 267, page 267, I used the example from there about the train to help us launch us into this discussion here. But rectangular approximation methods, RAM for short. We have left RAM, we have midpoint RAM, and right RAM. LRAM, MRAM, and RRAM for short. As you can see, I use the left points of each of these intervals. Okay, use those points as the heights of my rectangles. I could use the midpoints so that it goes through the midpoint of those intervals there, or I could use the right points. Right's going to be a little bit too much, left's a little bit too under. Midpoint, you get a little bit of over, a little bit of under both. Hopefully they cancel each other out. So this might be the better estimate right here. But you can compare these and get an idea for what a particular function, what the area under that curve would look like or be close to. So let's say we have a particle that starts at x equals 0 and moves along the x-axis with this velocity, v of t equals t squared, for the time t greater than 0. Where is the particle at t equals 3? Okay, well, to do this problem, we can use an estimate. So we can take and do we could graph this function, v of t equals t squared. Okay, and if we were to graph that on a coordinate plane from t equals 0 to t equals 3, it's going to start at 0 because at 0, the velocity will be 0. And it's a quadratic, it's just t squared, so it's a parabola, it's a quadratic function. So we're just drawing the positive side of a quadratic function. And at t equals 3, if we make a little chart here, v of t equals 0, we're at 0, because v of t is t squared. And at t equals 3, it's at 9. So let's find where it's at 1 and 2. Well, at 1, we plug 1 into that function. 1 squared, we get 1. We plug 2 into there, we get 4. So we've got some intervals here from 0 to 3. We got little sub-intervals here. We got 0 to 1, 1 to 2, and 2 to 3. So we've got 3 sub-intervals here. All right. Well, we can use these to help us estimate this. We could use we could do a left rectangular approximation. We could do an LRAM. If we use the left endpoints, basically what you're using, these are like your y values. They're your v of t. They're like your y values. So basically what you're doing is you're going to use those as the height of your rectangles. Because all of these pictures here, notice that the height of the rectangle is on the curve. Those are points on that curve. Those are function values, output values for that particular function. So if we do a left RAM, from 0 to 1, I get 0 to 1 here. Okay, from 0 to 1, this first subinterval, the difference is 1. So my rectangle on the first subinterval from 0 to 1, if we graph these points here, this is 1, 1, 2, 4, and 3, 9. The first rectangle, if I use the left point though, I'm actually not going to have a rectangle at all because I'm going to use 0 as the height of that rectangle. And the width of the rectangle, that's the difference in that's like how wide is your interval there. Well, we're going from 0 to 1, so the width is 1. Okay, I'm going to add that in. Okay, we're finite sums. Since we're working with finite sums, that means that we're adding up just a certain particular number of values. Okay, whereas an infinite sum would be something totally different. You would be adding up an infinite number of values, and that is a such thing, and that's not something that we're going to get to here in AB. All right, so at 2, we're at 4, but our left endpoint, the left value right here is 1. So I'm going to use 1 as the width of the height of my rectangle, and the width of my rectangle is going to be 1. Okay. we can see that an LRAM is going to be an obvious underestimate for the area under that curve, okay? Because we're missing a whole chunk here, and another chunk there of area. So this is going to be a total underestimate. At 2, the height of our rectangle is 4, and the width of that interval again is 1. So we've got 0 plus 1 plus 4, that's 5. So an LRAM would be 5, okay? If we did an RRAM instead, if we did a right rectangular approximation method, instead, we would use, instead of using 0, 1, and 4 as our heights, we would use 1, 4, and 9. We would still have the same width though. All of our little subintervals are 1, so we'd still have 1 as our subintervals, but we would have 1 times 1 plus 4 times 1 plus 9 times 1. And this would give us an estimate of 14, which is totally different. LRAM, RRAM, that's totally different. But if I were to draw that right rectangles in, I would have, obviously, it would be an overestimate of that area because I'd be having extra amounts of area here that's not really under that curve. Okay, so that's not a very good way of doing it either. So you could do a midpoint, figure out where the function is at 1/2, 1 1/2, and 2 1/2, and use those y values as estimates. And hopefully that would be an even better way of estimating that. But this is the way that you would be able to do these approximations. We're not interested just yet in finding that exact area. Obviously, we want to get as close as possible, but we will talk about later on in this chapter how to actually get the exact area under that curve. Okay, and that's going to be something a little bit different there. All right, the main thing is with using your estimates here, I want you to see that, for instance, I want you to see how good the estimates are, how to do these estimates. You know, how you're using, if I'm using the left endpoints of these are your heights, the function values are going to be the heights of your rectangles. If I do left endpoint, I'm going to use the left endpoint of each subinterval, the left y values right here. So I'm not going to use the y value that's furthest to the right. I'm going to use the ones on the left. If I do a right one, then I'm going to use the ones on the right end. So I'm not going to use the one that's furthest to the left. I'm going to use all these other ones. That's the main thing. And that, like I said, if we wanted to do an MRAM, we would have to actually find that function values at the midpoints. Okay, and we could do that. But to save some time, let's do that on a calculator. So let's graph this function. It's just a quadratic, just an x squared function. Okay, hopefully you can see that. It's just an x squared function. If I graph it, it's going to look like that. And we need to use the table, and we're going to find the values at our halfway points, 0.5, 1.5, and 2.5. We have 0.25, 2, and 2.25, and 6.25. And if we add those together, again, the widths of our intervals would still be 1. 0.25 plus 2.25 plus 6.25, we get 8.75. Notice that's in between 5 and 14. That's a lot closer, though. That's going to be a lot closer to the actual area under that curve. Okay. It's still not completely there, but it's a lot closer than what we had. Okay. So, all right. So that's how we're going to use this to find estimates. Now, the AP Calculus exam, they love to ask questions from this section as well. And a lot of times it'll be a table of data. They actually just give you a table of data. They don't actually even give you a function to work with. Sometimes you are given one where you're given a function. You get to pick your intervals then, if that's the case. And you get to pick it'll tell you in the question, on an AP Calculus question, find the left approximation, or left rectangular approximation, or right rectangular approximation of this. There's also another approximation method that we'll talk about tomorrow that they may ask you about as well to do, and you do that one a little bit differently. So, but they'll ask you how to do these with basically, they'll just say it in the question: right rectangular, left rectangular, or midpoint rectangular. I've seen more left and right though than midpoint necessarily, but if it was a midpoint one, hopefully it's a calculator question where you can use the table on the calculator to get your Y values. Otherwise, you're going to have the messiness of having to actually do that by hand, which is not terribly hard. You would just be squaring fractions. You'd be plugging fractions into the t-squared function then. All right. So I'm going to give you some questions where you've got some tables of data and you're going to calculate using these the rectangular approximation methods. You're going to calculate some of these values and be able to go through and actually find the area under the curve. You're going to answer some questions for me about this. And I'll also give you some problems where you may have to make your own table of values like we did with this example. If I give you a table of values, then you're set to go. You just go ahead and do like what I did here using those values. The left ones, you don't use the furthest right point. The right one, you don't use the furthest left point. You're going to just use the values that are in the table. I hope that makes sense. This is kind of a difficult section to really do virtually like this, but let me know if you have any questions.